All right. Hi and good day, everyone. So we shall continue our lecture on power dissipation. Okay. So our last lecture, we have discussed about this exercise. Just to recap what we learned. So we have P, which is the probability of switching, and alpha is actually the switching activity. Or we can go here. Then we can go back and then we see how do we derive the P dynamic and also P static. Okay, so we have learned about the element, the effect of power dissipation in the chip. Okay, which is very, very important. So we have two elements of power, which is dynamic, okay, and also static. Okay, so these two elements of power contribute to the total power dissipation, okay, in the CMOS circuits. So we have also discussed about between these two power, okay, static and dynamic. So dynamic is more dominant, whereby dynamic contribute more to the total power. So if the P dynamic is too big compared to the P static, we can ignore the P static and the total power will approximately equal to the dynamic power. So that's what we discussed before. And we also discuss about dynamic element of dynamic power. Okay, so under the dynamic power, okay, we have switching and also short circuit power. So between these two, short circuit power is less than the P switching lah. Most of the power comes from the switching. Okay, power dissipation comes from the switching power. Short circuit power normally happen during the transition of the switching lah. We have discussed this. Okay, whereby the transition between an on and off of the switch, okay, will unintentionally produce a short circuit current. When there is a short circuit current, there will be a short circuit power because P equal to IV. So when I short circuit multiply with the VDD of the chip, then we will get the P short circuits. So in most of the cases, P short circuit is very, very small compared to the P switching. And again, if the P switching is more than the P short circuit, we can neglect the P short circuit and the P dynamic is actually dominated by the P switching. If you go back to this equation, P total is actually mostly contributed by the P switching. Okay, so that's actually the what we call as the important keyword that we need to remember, right? So in exam, normally we don't give you the simple equation like P total equal to P dynamic plus P static. We don't give you these equations. You need to understand and memorize. Okay? This is very, very fundamental, very, very basic. We don't supply this equation in the exam, right? So P dynamic is mostly contributed by the P switching, and that's why, okay, as we discussed, okay, P dynamic equal to when we simplify this, we get CVDD square F switching. Okay, CVDD square F switching, right? Okay. So when we go further, we also have discussed about the probability P at node I. So P is actually probability. Pi is actually probability at node I. Okay, at node I. So we have discussed Pi bar equal to P1 minus Pi. So this also will not be given in the exam. So you need to memorize. So it's actually kind of inverted version of Pi, 1 minus Pi to get Pi bar. Right? And the relationship between Pi and Pi bar is actually this gives the what we call alpha I, or what we call as a activity factor. Okay, activity factor. So why is activity factor is very important? You go back to the equation here. Okay, P dynamic equal to CVDD square F switching. So F switching is actually we can derive from the main clock frequency. So F switching equal to alpha. Maybe we can derive from here. I think we have discussed this. So CVDD square F switching. So C VDD square F switching. Yeah? So maybe I use this one equal to C V V D D D, and then we have square should be complicated with n square. Okay, so maybe we need times 2 lah. Okay, V D D. Okay, C V D D alpha C V D D F switching F switching. Okay, so F switching is equal to alpha F. Okay, and that's why you see C V D D square F. Okay, so when we derive in the form of alpha F, okay, so F switching equal to alpha F. So then here we can see that alpha plays very important role in determining the dynamic power. Okay, right. So that's why it's very important to know how to calculate the F switch alpha value. Okay, so here is actually the F switching equal to alpha F. Okay, where alpha is actually the activity factor. Okay, all right. So to get the value of alpha is depending on the circuit that we use lah. For example, in this case, NAND gate. AND gate with 2 input. N2 means that AND gate with 2 input. Okay, so to get the alpha, so we need to calculate the PY first. So PY. So what is PY? So this is the AND gate, and this is Y, and this is A, and this is B. A, and this is B. So to get PY, P at node Y, so PY is PI, P at node I, so PY equal to PA, PB. So this is actually the equation. So PA multiplied with PB. So once you get the PY, okay, you can calculate the PY bar. Okay, so PY bar equal to 1 minus PY. Right? And then once you get this, you can calculate the value of alpha Y, whereby value of alpha Y equal to PY bar PY. Okay, remember we have the equation earlier. PI bar PI. So that's at node I. So in this case at node Y. So PY bar PY. Once you get the alpha Y, you can substitute inside this, and then you can use the provided value of C, for example, and then you can calculate the overall dynamic power of the circuit. Okay, so VDD normally 1 or 1 point something, and F is depending on the what we call the system or the desired frequency, operating frequency. Okay, the higher the F, the more the dynamic power, and that's why people try to reduce the element of voltage instead of frequency, because frequency very important to have a faster speed of our system, but the voltage we can try to reduce because the voltage has the factor of 2, power of 2. So if the voltage 1 or below, then we can have a circuit or a chip with lower power dissipation, right? So by this time, you should be able to explain actually the difference between dynamic and static power and derive the equation, okay? And also it has an ability to use this equation to explain further, okay? For example, in exam, if I ask you anything about the dynamic or static power, you can use the equation to help you in your explanation. That will give you extra marks, right? So that's how you answer just an example. Okay, so this is exercise. I think I told every one of you to do this exercise. Exercise number 1. It's number 1 or number 2? Number 1, I believe. Okay, exercise number 1. So this is straightforward. The dynamic power is defined as this one. Okay, so answer the following question. Following question. So derive the above equation. So this one, just recall back the earlier page where you derive until you get this. Okay, including using the F switching Okay, F switching equal to alpha F. So when you derive, so please include this at the end of your derivation, and towards the end you will get this. Okay, by using CMOS inverter with driving load capacitance, discuss the effect of dynamic power in electronic circuits. So this you can read in what we call in the textbook. Okay, we have lots of discussion on this. You can read in the textbook. The CMOS inverter, every one of you already know. CMOS inverter has a PMOS and NMOS. It have a load capacitance at the output side. So you explore it for you to explore. This one is at the textbook. Right. So this exercise we have done. I think this one we finished A, and B. I leave you all to do it. Hopefully. You all okay with this one? If you have any questions, just let me know. So this is exercise number 2. Exercise number 2. And this is exercise number 1. Okay. So for this is also related to actually exercise number 1 and number 2, sorry. Okay. But the difference is exercise number 3 here, I call number 3. You are given an equation in the form of Boolean expression. Okay, so this is the gate representation. A plus is actually the or AND gate. Any of you can respond? What kind of gate this one? Any volunteer? Plus or AND or what kind of gate this one? Can use chat box if you cannot use a microphone. What gate is that? That's actually the problem of online class. If we have face-to-face class, and then I can pick any of you to give the answer. The online class, they will take some time. Okay. So any try?
Question tadi apa all gate ke doktor?
Yeah. Okay. Thank you for the response. Thank you. Okay. So OR gate, and this is, I think this is exclusive OR gate lah. Okay. And then with bar at the top, NOR gate lah. Right? Exclusive NOR gate. Okay. So you can go to the diagram here, and then you can use this one. So in case in examination, you will be given this lah. Although this you can create on your own, but you will be given this one to avoid confusion among the student, right? So use this diagram to calculate the alpha, right? Right. So you can determine the value of the probability, okay, Px and activity factor as well. So first calculate the Px, probability at node X, okay. So this one, if you translate to equivalent schematic circuit, you can get the answer actually. So X actually, this is what we call exclusive OR, exclusive NOR. So I try because me myself also forgot already about the sign. I think this one, and then this is X, okay, X, and then A plus this one. So we have A, B, C. Try to derive on your own. You try to derive on your own. B and C, we have 3 input. B, A, B, C. I give you time. Maybe you want to try. Okay. So we have A, input A, B, and then C. Okay. So B and C is actually the exclusive. No lah. Okay. Then here you all them together. So I give you to try to get the answer. And then this becomes the output. Okay. You try exercise number 3. So we shall discuss. Right. So predict the probability. So you can calculate the Px here. Okay, so Px equal to alpha at, Px equal to, you go back to the equation before. So you get this one first, P not here. So for example, this PA, okay, is what we call maybe PBC. You can call PBC. And then you can get Px lah. Okay. So to get PBC, you go to the table. This one. Okay. X or, and then you invert lah. Jadi X no. Okay. I leave you all to do this. Then we shall discuss in the next lecture. Right. So to get the alpha activity factor, similarly, alpha at equal to Px bar Px, whereby Px bar equal to 1 minus Px. Okay. So Px bar equal to 1 minus Px. So from here, you will get the value of Px bar. And then you substitute here, and then you will get the alpha X. So alpha X is actually can be used to determine the power. Okay. So given also here, PA, PP, and PC, PA, P at A, P at B, and P at C equal to half. Okay, remember, use half instead of 0.5 because towards the end you will what we call truncate the value lah. Okay, if you use a point, floating point, you will truncate earlier, then the value will not be accurate, right? So once you get the alpha, okay, the alpha you substitute in this B. Okay, I just give you the way to solve. You calculate on your own. Okay, if the circuit area of X of this chip is 1.2 millimeter square. Okay, the size is 1.2 millimeter square, and the circuit operates at 2 gigahertz. So this is actually the F. Okay, here is actually the area A of the chip. Okay, with supply voltage, so see the VDD is less than 1 volt. So the VDD here, this is the VDD. Okay, VDD 0.9 with average switching capacitance of this is a value, so per millimeter square. So this per millimeter square you can get for a total of 1.2 millimeter square. Okay, when you calculate the C, total capacitance, okay, switching capacitance. Right, evaluate the dynamic power consumed by X. Use information provided in A to answer the question. So A is actually the to get the alpha. So basically P dynamic. Okay, it asks you to calculate the dynamic power. So P dynamic equal to P switching, okay, plus P short circuit, So P dynamic equal to P switching plus P short circuit. So in this case, you're not mentioned about the P short circuit. So we assume P short circuit equal to 0 or negligible. So we say that P dynamic, okay, P dynamic, sorry about my writing, P dynamic, P almost or approximately equal to P switching, whereby the equation of P switching equal to alpha X, okay, C VDD square, then F. Okay, so we have F here 2 gigahertz. Okay, substitute 2 gigahertz here, and VDD also given, which is 0.9. Okay, C also given, the value, the area multiplied with this one. Okay, and alpha also from A, and then you will get the value of the dynamic power. Okay, so straightforward, straightforward question. So any question? Any question from you all before we proceed? You can try using your own piece of paper and try to solve this problem during the asynchronous time lecture tomorrow. So we discuss a bit now, and then we do it tomorrow or after this, and then we shall discuss next week if you have any question. So if no question, we proceed to the next one. So this is what I mentioned just now, short circuit current. So P short circuit. So P short circuit normally happen when transistors, both NMOS and PMOS network, momentarily on at once. Maksudnya means that it's on at the same time. This is happen normally when the transition of the switch lah. For example, you have, I think we have discussed this. So this is just a revision. This is your PMOS. Okay, and then inverter circuit. This is your NMOS. Okay. Then this is your input. And this is your output. Okay, here is your VDD. And here is the ground or VSS. So when these two switches momentarily on, means that during the transition of on and off, it will produce actually a short circuit current. Okay, so short circuit current will actually flows from normally from the VDD to the ground. Okay, it flows from the VDD to ground. Sorry, from the VDD to the ground. So it will. We have I here I. Okay, this I will give the power what we call as a short circuit power. Okay, less than 10% of dynamic power if rise or fall time are comparable for the input and output. Don't worry about this one. The detail of this you can read in the textbook. What the most important thing here, you'll be able to explain what's happening when we say the short circuit current. Okay. Okay, this is another example. So I label this as example number 4. Example number 4. And this is very good for you to explore. Okay, I think this is pretty similar to this now. Okay, 200 million. M stands for million. So we have a chip. We have a chip. Okay, comprises of 200 million of transistors. So all together here, 200 million. And 20 million of logic transistors. So example, just I assume this is for logic and this is for memory. So 20 million, 20 M, okay, for logic, and the remaining 180, okay, 180 for memory, million for memory, 180 million for memory. So we have two different categories, logic and memory. Okay, right. So we have here the average width of the transistor 12 for this one. Okay, lambda 12 lambda. Okay, this is 12 lambda, and this one we have 4 lambda. Okay, in terms of the transistor average width. Okay, and the VDD is actually 1.2 volt. So this is actually VDD with 100 nanometer process technology, and we have gate capacitance of 2 femtofarad per micrometer. Okay, per micrometer, and alpha. See, alpha for logic gate. Okay, so alpha for this one. So the alpha for this one. So when you have this kind of question, so please use pen and paper to sketch like this one to figure out or to what we call imagine the value of the respective value for location. For example, alpha here we put as alpha L equal to 0.1. So let's say in exam, if you do this way, at least you will get marks, effort marks because you try to sketch something. Don't leave your answer with blank give you any marks. Okay, and then activity factor for memory. Okay, this one alpha M. So we label as M. M stands for memory, equal to 0.05. So from this one, you can imagine how do we calculate the dynamic power. Okay, so estimate the dynamic power consumption per megahertz. So remember, per megahertz. So per megahertz, so you know that the dynamic power equation, so P dynamic, Okay, or P switching. Similarly, we just use P switching. P switching equal to alpha C VDD square and then F. So when it's mentioned per megahertz, means that your F will be here, okay, per megahertz. That you just calculate this. Okay, to calculate this, you need to differentiate or isolate between the memory and also the what we call the logic. So alpha memory and alpha logic. Okay. Similarly for C memory and C logic. Okay, because they have different what we call lambda value of average transistor width with different 12 and 4. All right, so that's the idea. You may try on your own this one. Okay, so for this lecture, I give you what we call idea to do the exercise. Same to this one. Okay, and this one I think we discuss later. I want to maybe, I think that's all about the, this one you can read on your own. I think we almost finished. Okay, any question before we end? Okay, this one we do next week. We just do until this one first. Any question? If you have any question, just let me know.
No, Doctor.
Nurul Ain, thank you. Nurul Ain has raised her hand. Any question? So we'll stop the recording first.